All right, let's talk about one of the true unsung heroes of modern technology. I mean, it's a component that's hiding inside pretty much every single electronic device you own, and its whole job is to deliver a burst of power in the blink of an eye. You've seen it a million times, right? Picture a big event, tons of photographers, and with every single click of the camera, you get this incredibly intense, blinding flash of light that's over almost before it begins.
So, have you ever stopped to think about where all that energy comes from so fast? I mean, a camera's little battery is designed to provide a nice, steady stream of power, but there's no way it can just unleash that much energy all at once. So, what's the trick?
Well, the secret lies in this tiny but absolutely ingenious device that kind of acts as an energy middleman.
See, it isn't the battery doing the heavy lifting here. The real star of that split-second flash is a component called a capacitor. It's a device built for one specific purpose, to suck up energy and then release it in one single powerful burst.
So how in the world does it do that? Let's unpack its main function, and there's a really great, simple analogy that makes it all click.
Okay, so what is a capacitor, officially? Well, it's a device that stores electric potential energy and charge. You can think of it like a tiny temporary water tank for electricity. It takes a slow, steady trickle of energy from the battery and holds onto it, getting it all ready for a super fast release.
And this slingshot analogy just nails it. The battery is what provides the energy to slowly pull that rubber band back, nice and steady. The capacitor is that stretched rubber band, just sitting there holding all that potential energy. And then when it's time to fire, bam! It releases everything in an instant. Way faster than the battery could ever hope to on its own.
And believe me, these things are everywhere. They come in all shapes and sizes, from these little tiny ceramic discs and rectangles to the bigger cylinders you see here. They're hidden away inside almost all of our electronics, doing this exact same job.
So, how does this electric slingshot actually work on the inside? Well, let's take a look, because the design is just brilliantly simple.
You know, at its heart, a capacitor is basically just an electric sandwich. That's it. You've got two conductive plates, that's your bread, and they're separated by an insulating material, called a dielectric. That's the filling. And that's really the whole thing. That simple little structure is all you need to store energy.
So, how does the sandwich get its energy? It's a pretty straightforward process. When you connect a battery, it basically acts like a tiny pump. It pulls negative charges, electrons, off of one plate and shoves them onto the other. This creates a charge separation, right? One plate is now positive, the other is negative. And that separation creates an electric field between them. Now, here's the magic part. That field is where the energy is actually stored. You can disconnect the battery and that energy just stays there, trapped. The slingshot is officially loaded.
Now, how much it can store is measured by its capacitance, which we represent with the letter C. As you can see in the table, it's all laid out by the formula C equals Q over V. So C is the capacitance, Q is the amount of charge it's holding, and V is the voltage. The easiest way to think about capacitance is just as its storage rating. A bigger C means it can hold more charge for the same amount of voltage. Simple as that.
Now, of course, manufacturers make capacitors with a bunch of standard ratings. But what if you're an engineer and you need a really specific value for your circuit? Well, you can get it by combining standard capacitors in two basic ways, either in series or in parallel. And as you can see here, these two methods are completely different. Connecting capacitors in a single line, we call that in series, has a totally different effect than connecting them side by side or in parallel. Each approach changes the circuit's total storage capacity in opposite ways. So here's really the only thing you need to remember. When you connect capacitors in series, you actually reduce the total capacitance. Kind of weird, right? But when you connect them in parallel, you just add their values together, which increases the total. This gives engineers a super simple toolkit to build exactly the right amount of storage they need for any gadget.
Okay, so we've got a handle on what they are and how they work. But why does this tiny electric sandwich matter so much? I mean, what does it actually do in our daily lives?
Well, it turns out they are in absolutely everything. We already talked about camera flashes, but they are critical inside your phone, in the sensors that tell your car's airbag to deploy, in filtering signals for radios and TVs, and even in some of the most common ways we interact with technology every single day. Check out this clever use. A condenser microphone is basically just a capacitor, but with one plate that's super flexible.
When sound waves hit this little diaphragm, it vibrates. That vibration changes the distance between the two plates, which in turn changes the capacitance. The microphone's circuitry reads that tiny change and turns it into an electrical signal that is a perfect copy of the original sound. So cool!
And how about the screen you're probably looking at right now? Well, a modern touchscreen is actually just a grid of see-through capacitors. Your finger is a conductor, so when you bring it near the screen, you mess with the electric field of one of those little capacitors, and you change its capacitance. The phone's processor instantly detects exactly where that change happened and registers it as a touch.
So, when you get right down to it, capacitors really are the unsung heroes of our digital world. Whether a device needs a massive, sudden burst of energy, or it needs to sense the tiny, delicate change from a human touch, there's a very good chance a capacitor is doing the work behind the scenes.
And this brings us to one last, really fascinating thought. Remember, the energy isn't really in the metal plates or even in the charges themselves. It's stored in that invisible electric field between the plates. The field itself is the energy. And that leaves us with a pretty mind-bending question. If we can pack and release energy this way, what else could we power with just a field?